What an absolute honor to be among the very first people outside of Porsche to learn about the new 911 Turbo S, and alongside Patrick Dempsey no less. I started this channel with a whiteboard in my college apartment, and somehow fast forward to today and I've managed to bring that whiteboard to Weissach, Germany, inside Porsche's highly confidential development center, and not only learn from Porsche engineers, but teach Patrick Dempsey some math on the new 911 Turbo S. If you haven't yet watched the global premiere, you absolutely should do it, but in this video, we're going to be deep diving into the new engine and powertrain behind the new 911 Turbo S. Let's do this. So let's start off with the major powertrain differences between the last Turbo S and the new Turbo S. So both of them using a boxer 6-cylinder, previously 3.7 liters, now slightly smaller at 3.6 liters. Previously, they were using twin variable turbine geometry turbos. Now they have twin electric turbos, and they also now have added an electric motor between the engine and the 8-speed PDK transmission. So you have 701 combined system horsepower with the new powertrain versus 640 horsepower previously, both of them at 590 pound-feet of torque, though a much wider flat section of the torque curve for the new Turbo S, and a slightly higher redline at 7,500 versus 7,200. So looking at the two different torque curves, you can see they've greatly expanded the flat portion of the torque curve. So instead of peak torque only being available for about 1,500 RPM, now it's available for about 3,700 RPM. So they have more than doubled the width of this peak portion of the torque curve, so a much wider torque curve here, and this is looking at system torque. So of course the combination between the engine and the electric. So our engine is producing 631 horsepower, 560 pound-feet of torque. Our electric motor between the engine and transmission capable of 80 horsepower and 139 pound-feet of torque. Now, learning about this new 3.6 liter engine, you might think it sounds quite familiar, and that's true because it does share a lot of similarities with the 3.6 liter used in the new 911 GTS. Alright, so what's the same versus what is different with the GTS motor? So they are both sharing the same 3.6 liter boxer 6-cylinder. Same block, same heads. They're also using the same high voltage battery for the electric system here. 400 volt battery, 1.9 kilowatt hours. They're also sharing the same electric motor between the engine and transmission, and the electric motors for the turbos are also the same, except of course now we have two turbos instead of one. Now, aside from that, a lot of differences here. So the intake and the exhaust are completely different. We've got two throttle bodies instead of just one, because we've got an individual turbo for each cylinder bank. Of course, two turbos instead of one. The turbos, while they use the same electric motor, they actually have smaller diameter wheels for the turbines and the compressor, and they are making more boost, and because they're using these smaller wheels, they're able to spin faster. To create that higher boost, they spin about 20,000 RPM faster than the turbo used on the GTS. You also have different pistons used with the Turbo S. They've got a 9.5 compression ratio versus a 10.5 compression ratio on the GTS's Boxer 6. And you of course have a lot more power now thanks to the additional boost and the two turbos. So 631 horsepower versus 478. And you have more power from the electric motor. And you might be wondering, well, how would you have more power from the electric motor if they're both using the same battery and the same motor? Well, the reason for that is, as you're spinning up these two turbochargers, you can pull energy from the exhaust out and redirect that energy directly to that electric motor. So because it has two turbos, it's able to regenerate more power from the exhaust and send more power to that electric motor. So higher peak power from both the engine and the electric motor. Now, these electric turbos enable another clever benefit, and that is they eliminate the need for wastegates, just like what is done on the GTS. Alright, so how does this work? Well, let's look at a traditional turbocharged engine. So you have air come in through the compressor side, go into your engine, combust, those exhaust gases go out, spool up a turbocharger, and then leave through the exhaust. Now, as you spool up that turbocharger, it means you pull in more air, make more exhaust, spin this faster, and it just keeps cycling and it keeps getting faster and faster and faster, and you make more and more boost, right? So how do you limit that boost? Well, you have a wastegate. So you have a valve that opens up and you enable some of that exhaust to bypass the turbine and the turbocharger so that you can have that boost set at whatever you choose. Now, if you have an electric turbo, you can eliminate the need for this entirely. Now, how does that work? Well, as that turbocharger is starting to spin up faster and faster and faster, How do you limit boost then from getting higher? Well, you use your electric motor as a brake. So you regenerate energy, use this electric motor as a brake, slowing down that turbine to whatever speed you want for whatever boost level you want. So a very clever solution, and then you can send that power to the battery, or you can send that power to the electric motor, sandwiched between the engine and transmission, and get more power to the wheels. Now, there's another really cool benefit of this, and that can be explained by looking at what happens when we completely run out of energy in our high voltage battery. Now, that's really not realistic. There's going to be plenty of times where either this electric motor or these turbos can be recharging this battery, so it's not something you really have to think about. But let's say you were doing a top speed run, so you're just flying down the Autobahn, you're sitting at 200 miles per hour, so of course if you're at full power constantly, eventually that battery is going to drain, right? Well, you aren't limited to your engine's power in this scenario. So the engine can make 631 horsepower, but you have more than that. Why? Because both of these turbos are still regenerating power from your exhaust gases and able to direct that power directly to that electric motor. So your actual power is boosted a little bit up on the top end through regeneration using these electric motors within the turbocharger. How clever. And of course there's a greater effect here on the Turbo S versus the GTS because of those two turbos rather than one. Now inevitably when you start discussing combustion engines combined with an electrification strategy, people say, oh, it's too complicated, won't be reliable, blah, blah, blah. The thing is, start to think about what this electrification strategy means you can eliminate from the system. So people say, oh, it's too complicated. Well, think about previously they're using two variable turbine geometry turbos. These are really complex turbos in comparison to a much more simple design on these electric turbos. You've eliminated the need for the electronic wastegate, so you're getting rid of that and just using the electric motor to do it. You don't have an alternator anymore because you can use that motor between the engine and transmission. You now have an electric AC compressor, and Porsche's dynamic chassis control is now controlled by the 400-volt system, so you've eliminated your accessory belt entirely. You also don't have to use a starter motor because you've got this electric motor there. So there's a lot of complexity that you can actually take out of the system as a result of the electrification strategy here. So the electrified strategy, of course, has very obvious performance benefits, but it also has emission benefits, and that brings us to lambda equals 1. So this engine must run at lambda equals 1. Well, what does that mean? Well, it means it needs to run at the ideal air-fuel ratio. So burning all of the fuel, all of the air, the exact ratio you would need, and the reason for that ratio is because it provides the greatest efficiency for your three-way catalyst to break down things like carbon monoxide, hydrocarbons, and nitrogen oxides. That's where a three-way catalytic converter operates at its most efficient point, at this air-fuel ratio. So if you were to run less than lambda equals 1, of course you'd be running rich. If you're running greater than lambda equals 1, you're running lean. Running rich has its benefits, right? It means cooler cylinder temperatures. This means less chance of knock. You can run advanced timing, and this means you make more power. So if running at lambda equals 1 equals less power, how do you compensate? Well, Porsche says you would need about 20% more displacement to make up for it. So for example, going from a 3-liter to a 3.6 liter. But there are many ways to combat this power loss and still operate at lambda equals 1, and one of those solutions is an electric turbo. So by running an electric turbo, you can run a much larger turbo without the drawbacks. So if you run a larger turbocharger, well, you're going to have less back pressure. That de-throttles the engine. It allows you to have cooler cylinder temperatures and a better burning behavior, and so you can run at that lambda equals 1. And because you have an electric motor here, you can use that to spool up this large turbo at low engine speeds, so you can have boost on that low end, and you don't have to worry so much about turbo lag with a big turbo because you use that electric motor to spool it up. So does this solution actually work? Well, let's look at the 911 GTS as an example, which went from a 3.0 liter to a 3.6 liter, and yet they make very similar power. Now, you might blame this increase in displacement on lambda equals 1, but the Turbo S is making significantly more power than the GTS with the same 3.6 liters of displacement. So on a power per liter basis, the GTS could have still made equivalent power to the previous generation while running a 3.0 liter. Hey, more room to play for the tuners out there. And the Turbo S is now actually making more power per liter than its predecessor, despite continuously running at lambda equals 1. So clearly, the electric turbo, among the other lambda equals 1 strategies implemented, is an effective solution. To me, this is why engineering is so cool. You're provided a rule set, and then you have to create a solution that follows those rules while still achieving all of your performance goals. So the rules for emissions have gotten harder and harder. I guess people like breathing. Yet Porsche has found a way to give the powertrain more power, a much wider torque curve, significantly less turbo lag, and it's now 14 seconds faster around the Nürburgring than its predecessor. Incredible! Now, there's some interesting backstory behind this video as far as why I was involved with the global premiere of the new 911 Turbo S and filming alongside Patrick Dempsey. And so that it's clear, because some folks may ask, this video you're watching right now is not in any way sponsored. Now that said, I was paid for my role in the premiere, starring alongside Dempsey, and what an absolute honor. But why that happened, why I was part of the premiere, goes back to my video on the new 911 GTS engine and their strategy with the electric turbo. Internally, an engineer at Porsche told Porsche Communications that the video I did was really well done. They said that if anyone wants to understand the system, they should just watch that video. There is truly nothing more warming to hear, because these are the people that I respect so much. The engineers who work behind the OEMs. And so Porsche was like, hey, the Turbo S actually has many similarities. Why don't we bring Jason on for the premiere for it, since he did such a great job with the GTS video? Now, my role during the premiere was pretty funny. Essentially, Patrick has gone through a lot of technical discussions about the car, and he's told he can finally go out and drive the thing. But there's a catch.
Oh. More theory.
I'm standing between him and the car, with a whiteboard full of math, the last hurdle before he can get behind the wheel. So intentionally, and actually at my request, he's meant to appear pretty uninterested. Because would you rather learn about complicated math or just drive a 911 Turbo S? So there's a bit of a montage of me explaining to him how to calculate the new 911 Turbo S's 0 to 200 to 0 km/h time. But from my end, it had to be real. I spent over a week developing a model, creating a Riemann sum, and finally boiling it all down into a single equation that, once I had all of the variables provided by Porsche, I could give my estimate as to what the 0 to 200 to 0 time would be. When I landed in Germany, Oliver Hilger, global spokesperson for the 911 model line, asked me what time I thought it would do it in, as it had not yet been tested. I told him 12.7 seconds. 2 days later, they tested it on the track, and as revealed in the global premiere, it did it in 12.6 seconds. None of this was pre-planned, that's just exactly how the numbers landed. However, the premiere only includes a taste of how I reached my 12.7 second time, so I wanted to show the whole video for anyone that was curious how I calculated it. Here's the full breakdown. So Patrick, I'm going to teach you how to calculate the 0 to 200 and back down to 0 km/h time for the new 911 Turbo S. You might wonder, why are we trying to figure this out?
Yeah.
So this is a good way in one test of determining how quickly a car can both accelerate and how quickly it can brake. So there's two fundamental equations that are really driving all of this. And the biggest one that you have to figure out is velocity equals acceleration times time. This is our main driving equation right here, because we're trying to find out time, right? So to prove to you that this is accurate, velocity, meters per second, acceleration, meters per second squared, multiply that by seconds, time of course, gives you meters per second. All right, so we believe the initial equation. Time is what we're trying to figure out. Time, we can divide acceleration on both sides, so time is equal to velocity divided by acceleration. All we're trying to figure out is this t right here. We know our change in velocity already. It's 200 km/h, right? So the only thing we have to figure out is A, acceleration. You're following, right?
Yeah, no, I got you. I'm with you.
So what is acceleration? That's the only number we have to find out. Well, force is equal to mass times acceleration. We know this from Newton. It's his second law of motion. So if we solve this equation for A, because that's what we're trying to figure out, acceleration equals force divided by mass. Okay, great. That's all we need. Now, the thing is, there's a lot of forces. So the car, of course, is trying to accelerate the vehicle with the traction force. And we want most of that to go into linear acceleration, this F equals ma equation. That's where we want all of that traction to go. But unfortunately, there's other forces acting on the car. So we've got the force of aerodynamic drag. Of course, you're trying to push through the air. You've got the force of rolling resistance. So the tires are absorbing energy as you're driving along. They're taking away energy from accelerating the car. If by chance you're going uphill, you of course have gravity to worry about. So the force of whatever grade you're driving up. You then of course have linear acceleration, which we've just discussed. And then you also have angular acceleration. So things like the wheels, the tires, the brake rotors, the drive shafts. Not only do you have to move these a certain direction, but you also have to spin them up, right? So that takes energy to spin them up.
Right.
But we want all of it really, this is what we're trying to maximize here. So we will solve this equation for this one right here is equal to mass times acceleration. That's the A we're looking for. So we need to solve all of this for that A. Now, I assume I probably don't need to go through every one of these equations. You're probably familiar with these?
More or less.
More or less? Okay, great. So we can move on from these. The one caveat here being that angular acceleration, realistically, you want to take the moment of inertia, multiply it by angular acceleration, divide that by the radius, but that's very complicated. You have to add up all the different parts that could possibly rotate on this car, so we're just going to use a linear approximation, take a percentage of our linear acceleration. Right? All good. So we're solving this for this A. We want to figure out what this A is in this equation here. So we're going to ignore and we're going to say we're on a flat surface, so we don't need to think about gravity pulling the car downhill.
Right.
So we've got aerodynamic drag, we've got rolling resistance, and then we've got our linear and our angular acceleration.
Okay.
So we solve this equation for A. Again, that's what we're trying to figure out so we can get time. And that gives us our traction force minus aerodynamic drag. We've got this beautiful equation right here. Now, this equation is based on two things. It's based on gear ratio, because of course our traction force, if we're in a lower gear in the car, say we're in first gear,
right,
we have more torque going to the wheels than if we're in second or third gear.
Right.
So we have to base this on a specific gear, and then also we have to base it on a specific velocity, because as you're traveling faster and faster, then you have more aerodynamic drag. So you have to keep that in mind. Okay, so now that we have the equation for A, we know our velocity, we can solve for time, right? Time equals velocity over acceleration. We know what A is with this equation here. So let's just do a quick example, and then we'll kind of get into some calculus, which will be exciting.
Yeah.
So, quick example. Time is equal to, let's just say we're trying to figure out how much time it takes to get to 1 kilometer per hour. We're starting at 0. How long does it take to get to 1? So we need to convert that to meters per second, so we just divide kilometers per hour by 3.6. And then we're going to say that our acceleration equation popped out, and we got an acceleration of 1.2 Gs that we were able to start with. So we multiply that by 9.81 meters per second, and we get a time of 0.02 seconds. So the total time that it took to go from 0 kilometers per hour to 1 kilometer per hour, 0.02 seconds. Are you with me so far?
I kind of lost you in the last bit, but I'll catch up. Go ahead.
Okay, great. We won't restart.
No.
Now, we're just going to use this same logic and go from 1 to 2, right? We already went from 0 to 1. We'll go from 1 to 2. We'll go to 2 to 3. We'll go from 3 to 4, and so on. This is actually called a Riemann sum. It's a German mathematician, conveniently. Here we are.
There you go.
And so we're just going to be adding up all these little chunks of time.
Right.
So what's cool is if you plot this, so one of the ways of thinking about time is rather than velocity over acceleration, the inverse of your acceleration, 1 over acceleration times velocity. So if we look at a graph and we plot the inverse of acceleration with respect to velocity versus velocity, you get this green line right here. And what we were doing is we were taking these individual little chunks, we're just saying, hey, from 0 to 1, that's a certain amount of velocity change, and we multiply that by the inverse of our acceleration function, and that gives us this block right here. What is this block right here?
I have no idea.
It's a little chunk of time.
Okay.
So all we're doing is we're just adding up these little chunks of time. We're finding the area under the curve. This is like baby calculus. It's pretty cool because you're doing like calculus but by hand. You're not doing it like the real way. You're doing it like an easy way in like the 1800s by this German mathematician. So you're adding up all these little blocks. So if we just go from 0 to 200 and we add up all these blocks, we get a time, right?
Okay.
But there's a flaw with this thinking.
Oh.
Because as you can see, there's little spaces above these blocks that we're not accounting for. So how could we calculate what these little spaces are? Well, we need to make our blocks thinner. So if we use thinner blocks, if we use narrower bars here, you're finding an area and you're filling in these little gaps with these narrow blocks. So what's ideal? Well, ideal is infinitely small blocks in width, and then you multiply them by this equation here, and that gives you the area underneath the entire curve. So that is calculus, that is integration. So that's where we are right here. So integration is finding out the total area under the curve. And so that's what we want in order to get the best guess of what is this acceleration going to be. So time is equal to the integral of our velocity from one point to another of the inverse of acceleration with respect to velocity, right? But as I mentioned earlier, this changes based on what gear you're in. So you have to do it for gear 1, you have to do it for gear 2, you have to do it for gear 3, and then in 4th gear we can finally reach 200 kilometers per hour. So we have to do it for all 4 of those gears. Well, there's another problem still. Do you have an idea of what it is?
I'm not in the car?
Yeah, not yet. Now, the problem is that this first equation could be optimistic. So in first gear, often you might have more traction, or you might have more power than you have traction.
Right.
So because you're traction limited, it's a different equation.
Exactly.
It's much more simple. Time is equal to the top speed of your first gear divided by the frictional coefficient of your tires multiplied by gravity. Okay, so once we've totaled all of these integrals up, we get the total time for acceleration, and that gives us our 0 to 200 time. So we're halfway there. How we feeling?
I'm good. I feel good.
All
Feel
right,
great.
great. So all we have to now figure out is the braking time. And actually, it's not too bad to figure out, because braking really comes down to the tires, and that is going to be the biggest factor in what is that stopping distance. So if we know our frictional coefficient of our tires, multiply that by gravity, we have, once again, velocity over acceleration. So velocity over frictional coefficient times gravity, that's going to give us our braking time.
Right.
Now, we add our acceleration time to our braking time, and you're looking at all this and you're saying, Jason, this is all just letters, right? There's no real numbers here.
Right.
Right. So this is the better way of teaching it, but Porsche actually provided me anything I put a little blue star next to. Porsche provided me these numbers, and then anything with a green star, I came up with my own estimate based on, looking at other cars out there and trying to figure out what would be a good number for that.
Right.
So, using the actual numbers from Porsche as well as some of my own estimates, we take our total acceleration time, we take our total braking time, we add them together, and what do we get? 12.7 seconds. That's going to be our 0 to 200 and back down to 0 time.
Okay.
Now, do you want me to run through it one more time, or do you feel like you got it?
No, I'm getting a grasp of it.
Okay, great. Closing out, again, what an honor to be a part of something like this. I feel very fortunate, and Porsche and Patrick Dempsey were truly incredible to work with. If you have any questions or comments, feel free to leave them below. Thanks for watching.